Okay, this is Dr. Brown. In this short video, we're going to talk about the precise definition of a limit. Now, previously we calculated a lot of limits, and you all have a very good intuitive feel about what a limit is. In this particular video, we're going to talk about a more precise definition of a limit. Before we define a more precise definition of a limit, we're going to define some symbols. First, there is a symbol epsilon. It's a Greek letter epsilon. And then there is the Greek letter delta. And now we're going to get into the definition of a limit. First, let's let f of x be defined on an open interval about the number x naught, except possibly at x naught itself. In other words, it's possible that f of x naught may not be defined, although most often it is. So we say that the limit of f of x as x approaches x naught is the number L, and then we write, as we've been writing, the limit of f of x as x approaches x naught equals L. And this means that if for every epsilon more than 0, there exists a corresponding number delta that's also more than 0, such that for all x that is within delta of x naught, that this implies that for those values of x, f of x minus a limit will be less than epsilon. In other words, if you get x close enough to x naught within the delta that you pick, then the difference between f of x and the actual limit is less than the epsilon. Let's try to illustrate that a little bit here. Suppose that the limit of a function is L, and you know that, and someone gives you an epsilon that could be very small. What you do is plot L plus epsilon and L minus epsilon, and then you need to then find a value of x such that if x is within delta, notice that this distance is delta. If x is within delta of x naught, then the corresponding value of f of x will be well within epsilon of the limit. So let's look at an example. Suppose we have this function, and someone gives you an epsilon equal to 1/10. So you plot out L plus 1/10 and L minus 1/10, and then you go back for L plus 1/10 and find out what value of x corresponds to L plus 1/10. Well, that's basically finding the inverse function and calculating the inverse of L plus 1/10. So when you do that, you get an x upper, and which turns out to be a certain distance above x naught. Then you go and you plot L minus 1/10, go backwards and calculate an X lower, that you see is within this distance of X naught. Then you pick the smaller of the distance between the X upper and X naught, and the distance between X naught and X lower, and of course that would be the blue region here. And you pick an uniform interval around X naught. And so if X is in the blue region, you can see from the function that, for instance, if you pick this to be X, then f of X is going to be within epsilon of L. Now suppose they say, well, you beat me on 1/10. I'm going to give you an epsilon equal to 1/100th. You do the same thing. You do a plot of L plus 1 over 100 and L minus 1 over 100. Go backwards and get an X upper, and also get an X lower, and then pick a delta. And in this case, the delta would be the smaller of the intervals. And so if you pick X within delta of X naught, the value of f of X is going to be within epsilon of the limit. And then you could keep on going and say, well, somebody might pick 1 over 1,000, and no matter how close or how small an epsilon they pick, you can always go backwards and find a delta such that if you're within delta of X naught, f of X is going to be less than epsilon distance from L. And you could keep on going to 1 over 100,000, and you sort of get the picture. You squeeze in what your value of delta will be, but you'll always be able to get a delta such that if X is picked within delta of X naught, f of X minus L, the distance is from L is going to be less than epsilon. So this suggests a procedure which we will write down on the next page. But if someone gives you an epsilon, you plot L plus epsilon and L minus epsilon. You then use the function and use it to calculate the inverse of L plus epsilon and calculate an X upper, and then go backwards with L minus epsilon and calculate an X lower. Both of these would be the inverse function of L plus epsilon or L minus epsilon, and then pick the smaller of these intervals. The way this is drawn, this is the smaller interval, and therefore delta would be that distance. So that suggests this procedure to calculate a delta for a given epsilon. You calculate L plus epsilon and L minus epsilon. So the X lower would be the inverse function of L minus epsilon. We'll show you how to calculate the inverse in a moment. And the x upper will be the inverse function of L plus epsilon. In other words, we're going backwards from y to x. And then we choose delta as the minimum of x upper minus x naught, or x naught minus xl. And then the interval we're talking about would be x naught minus delta to x naught plus delta. On the next slide, we've got an example. We have a function of x equal to square root of x minus 1, and we're finding the limit as x approaches 5. Well, you can see very easily that the limit can be calculated by just plugging in x equal 5. F of 5 is equal to the square root of 5 minus 1 is equal to 2. So we know the limit is 2. So we draw a sketch of the function y equal to square root of x minus 1. We put the limit 2. And if someone has given us an epsilon equal to 1, this is just an example. Someone gives us an epsilon equal to 1. We calculate L plus epsilon is equal to 3. L minus epsilon equals to 1. And so we want to find out what value of x produced y equal 3. Well, y is equal to the square root of x minus 1. And we know the y is equal to 3. So squaring both sides, we get x minus 1 equal 9, or x equal 10. That tells us that x upper is going to be 10. Then we calculate the x lower by plugging in L minus epsilon equal 1. So we've got the square root of x minus 1 equal 1. Squaring both sides, we get the square root, we get x minus 1 equal 1, or x equal 2. So x lower is going to be 2. Now, since x naught is 3, we notice that the distance between 2 and 5 is equal to 3. The distance between 5 and x upper, which is 10, is 5. So we pick the smaller of the two to be the delta. So we pick delta equal to 3. So if anyone picks a value of x within the blue region here that's within 3 of x naught, it's easy to see that the f of x will be within epsilon of the limit 2. Now, if someone wanted to pick, say, not an epsilon of 1, but an epsilon of 0.1, we can then go in here and squeeze in on the epsilon, and L plus epsilon will be 2 plus 0.1, or 2.1. So we plot that on the graph, and then we do L minus epsilon, which is not 1 in this case. L minus epsilon would be 1.9. Now we have to go backwards and find out what value of x produce the 2.1. So since y is equal to the square root of x minus 1 equals 2.1, we can solve this for x and get x minus 1 equal 2.1 squared. And this value is 4.41. And so x is equal to 5.41, the x upper. And now we look at what x lower would be and plug in the square root of x minus 1 equal L minus epsilon, which is 1.9. Now solve for x, and we get x minus 1 equal 1.9 squared. And that is 3.61. And so x is equal to 4.61. And so now we plot x lower and x upper, and we see that we pick a delta as a minimum of 5.41 minus 5. That's this distance, which is 0.41. And we also need to calculate 5 minus 4.61, which is 0.39. So we pick the minimum of 0.41 and 0.39, and so we pick delta is equal to 0.39. So if we choose an x within 0.39 of 5, then we are assured that the value of f of x minus a limit, which we know to be 2, is less than the epsilon, which in this case was 0.1.